let me know.
It's okay.
Okay, again, good morning, everybody. My name is Sol Carretero Palacios. I'm from the Autonomous University of Madrid, and I'm going to start chairing this session today. We will start very fast because we have a very short time for the first speaker. He's Joseph Garrett. He's instead of Jeremy Munday, and he's going to give a flash talk about the results, and then we can ask him some questions about the work. So when you want, Joseph.
Hi, can everyone hear me?
Yes.
All right, cool. I'm Joe Garrett. I'm a former student of Jeremy Munday. I was in his lab when we were doing these experiments. So when he couldn't make it, he called me up and said, "You're in a better time zone for this. Can you give the presentation?" So I said, "Sure." All right. Oh, the Zoom is a little bit weird on this, but I'll try to get it to work. So the main thing we did that I worked on there, does it look a little better now? We'll do it like this. The main thing I worked on was atomic force microscopy measurements of the Casimir force. We had a setup where we had a cantilever on a sphere. We changed the separation between a plate and the sphere, and at different separations, we would shake the lower plate and look at the response of the sphere and try to estimate the force from that. This technique was originally developed by Svindeman and another group about 10 years ago, but we made some of our own developments and used it for several measurements. I'm going to be going fairly quickly, so we have time for questions, but I have just a few slides before we begin those. One of the main things, this is a little awkward, one of the main things I worked on was looking at the sources of experimental error in this sort of measurement. So we looked at the shape of the probe. We found that they were very spherical. So we did some fitting of the sphere to a circle and saw how much the radius deviated around these particular glass spheres. We looked at the effect of laser interference when we were making the measurements. And that was a fairly large effect. We looked at the thermal drift over time on how we could deal with that. We looked at the drift in the laser diode position. We looked at drift in the lock-ins phase. And here, it was kind of annoying to work with, but we found a way of mitigating it. We looked at electrostatic patches and how well we were actually mitigating the total electrostatic force. We looked at the effect of drag because we were doing these measurements in air. And we looked at a lot of other things as well. So we tried to combine them all, and you can see this plot in the lower right-hand corner. For a particular experiment, we tried to estimate what the uncertainty as a percent of the force was for several many different separations. And so these various contributors to the total uncertainty vary from experiment to experiment, but on the whole, it's the same group. We also looked at some patch potentials and Casimir force experiments. I'm going to just go a little more quickly so we have time for questions. Basically, we found that on some surfaces, if you didn't prepare them carefully, they ended up extremely patchy. But if you were more careful, you put down a blocking layer, you could make them less patchy. And then we computed what the force would be between a sphere and a plate for these different patches for many, many different orientations. So this is a little something that wasn't in Jeremy's talk that I added. In order to do all these computations with the patch potential force, we put together some code that can run through them pretty quickly. For the paper, we had done about 10,000 different sphere plate orientations. And each of those at, I think, 21 separations between the sphere and the plate. This code has a tutorial, And hopefully, my hope is that other experimentalists who are able to quantify their patches can quantify the force from them a little bit more easily with this. And then I wanted to note with patch potentials, there's a paper from 2003, Speak and Trunkel, that gives the main force from patch potential equation. And it writes it in terms of case-based representation of the patch potentials, and in terms of the autocorrelation function between the plate in itself, the sphere in itself, and the correlation between the two of these. In the first paper we had written on patch potentials, we simplify this equation by assuming that there were no correlations in the patches between the sphere and the plate. But we found out in the course of doing numerical calculations that this autocorrelation function essentially doesn't vanish if you have a regular micron scale size sphere. So if it's 40 microns radius, this autocorrelation is not going to vanish. And one really strange effect we found was that sometimes this capacitive force can be repulsive. Particularly, the easiest case to see is if all the autocorrelation functions are the same, which is a reasonable case because you could just have the exact same pattern of patches on both surfaces. In that case, you get a repulsive force, which is strange because this is coming from capacitances. And so at this point, I just want to emphasize that these patch potentials are interesting in their own right, in addition to being an experimental artifact. This is the lab when I was there. I guess you can see me. And here are some of the papers that our group published that I didn't think I'd have time to talk about in this flash talk. All right, and that's everything. I think that was very flash. So sorry about the speed. But I am open for questions. How do I read those or get those?
Okay, so I think you can read these questions. Thanks, Joseph. Should I read them for you, or
are they just in chat? Oh, I see them in chat.
In the chat, yeah, but we should say it aloud.
I can. So Karsten Henkel asks, for what reason is C12 not 0? I don't know that there's ever a reason for it per se, so much as when you just are working with small samples, so there are only a few patches on the surface relative to the size of the sphere, some correlations just emerge. I don't think that there's any physical thing causing it other than a finite size sample. There could be, but I have no evidence of that.
Okay.
Are there any other questions? I only see that one.
I have a question myself.
Okay.
Because I'm the host today, I'm going to say it loud. This is about the talk, the full talk. When I saw the new samples that they were preparing, maybe you don't know this now, no? But what were the materials that you are using in the new samples? They were growing rings and arrays of some structures. What is the material and what do you expect to see in these new geometries?
So all of those are coated with gold in the end. So they're coated with the same layer of thickness of gold that we have here. As far as the material itself that's under the gold, I'd have to look that up. It was some weird polymer-based thing that you could harden.
Okay.
But I don't remember it off the top of my head.
But okay, it's again gold. Okay, thanks. Any other question? If not, since we have to be very strict with the schedule, I will change to the new speaker. Okay, so thanks, Joseph.
Yeah, thank you.
Bye. So the next speaker is Castillo Lopez, and she's going to give another flash talk for us. So whenever you want.
Thank you. Can you see my screen?
No, we cannot
No,
see
we
it yet.
can't.
I have the permission.
Yes.
Okay. In the share screen option, I have one participant or multiple participant.
If you click on the green button, just share screen.
Yes.
You have more than.
Yeah. Okay. Can you see my screen?
Yes, now
Yeah,
yes.
now yes, we can.
Okay. Thank you. Okay. Well, good morning, everybody. My name is Shunashi Castillo, and the topic of my talk is near-field radiative heat transfer between high-density superconductors. We studied our system consists of two semi-infinite slabs of high-density superconductors separated by a vacuum gap. We use yttrium barium copper oxide optimally doped with a critical temperature of 93 Kelvin. The crystalline structure of this compound is conformed of AB planes of oxygen and copper. And we describe the dielectric function of these AB planes using a two-fluid model. In the normal state, the dielectric function have this form with Drude contributions associated to free electrons. And additionally, there is a contribution of a near-infrared band and 6 optical phonons. In the superconducting state, we model the dielectric response as the equation 2, where the Drude is condensed into a delta function. Here, I show you the real and the imaginary part of the dielectric function. You can see that as the temperature decreases below the critical, the real part becomes more negative and the imaginary part diminishes. Okay, we study 3 different cases. In the first case, both plates are in the normal state. In the second case, one is in the normal and the other is in the superconducting state. And in the third case, both plates are in the superconducting state. Here I show you the first case of 2 normal YIPCO plates. I show you the energy transmission coefficient for P and S polarization. If we analyze the P polarization, we can appreciate the interplay between different terms of the dielectric function. When if we analyze separately, the Drude term would allow the excitation of a gap surface plasmon polariton, and in the same frequency range, near-infrared electrons contribute to the energy transmission coefficients. So there is a competition between these two modes, and they form a new guided damped mode. This new guide damped mode also hybridizes with optical phonons and low frequency, as you can see in the inset of the figure. And in the case of S polarization, we only found the excitation of frustrated phonons polaritons. If we decrease the temperature of one slab and the slab become to the superconducting state, we found that the energy transmission coefficient at low frequency is suppressed, and this suppression is enhanced or is stronger if both plates are in the superconducting state. Here I show you the spectral heat flux as a function of the frequency for the 3 cases. For the normal superconducting and superconducting slab, you can see that the superconducting transition produce the drop-off of 2 orders of magnitudes of the heat flux. And if we integrate this heat flux, we obtain the total heat flux. And here I plot the total heat flux as a function of the separation between the slabs. And we obtain that for a fixed value of the vacuum gap, the heat flux decrease of 2 orders of magnitudes when both plates are in the superconducting state. Finally, I show you the total heat flux as a function of the temperature of one slab. We fix the temperature of one slab at 120 and vary the temperature of the second slab. You can see that as the temperature of the second slab decreases, the heat flux increases up to the critical temperature. Here the curve have a change in the slope and decreases with the temperature. If we calculate the derivative, we can see a discontinuity at the critical temperature, and at sufficiently at enough small temperature, the derivative is constant. That means that the heat flux is proportional to the square of the temperature. Okay, I want to conclude with these ideas. When both plates, we found that in the normal state, polarization energy transmission is enhanced by guided damped mode and funnel-like resonances, and less polarized frustrated mode polaritons are present at low frequencies. And when at least one of the slabs is in the superconducting, several modes can no longer be excited, and this decreases the heat flux by 2 orders of magnitudes. And the differential calculation of the heat flux shows a discontinuity, signaling that there is a phase transition due to the superconductivity. Okay, thank you for your attention.
Okay, thanks, Nashi. Are there any questions, please? Well, this is, no, sorry. No question. Okay, I have a question. I'm not, so the aim of this mini colloquium is to bring together Casimir and heat transfer communities. So I'm not so familiar with heat transfer, but maybe you can answer this. So it seems to me that, so I've seen many times that plasmonic structures are used for enhancing heat transfer, but here it seems to me that when you excite a plasmon mode, then the heat transfer is minimized. Is it like that? And why do people then use, so would it be better to not excite the plasmon in this case?
Okay, in this case, the heat flux is reduced because of the superconducting transition. Okay, because when you pass to the superconducting transition, some part of the electrons condense, and there is less, the plates become more reflective and cannot be excited as plasmonic modes that in another condition would enhance the heat flux. But you are right, plasmonic materials enhance in normal, in other kind of materials, the heat flux, but in this case of superconductivity, is not the case.
Okay, thanks. There is another question from Karsten.
Okay.
A technical question. The dielectric function in the superconducting phase has funny singularities. How are these inserted into the reflection coefficients? I guess, well, maybe this part, you can also read it because
I cannot
a bit
read
longer.
the...
No, the chat,
Okay.
okay. So it's in the chat. I
Okay.
guess that one takes the formula for RP, say, considers a Drude model with a finite damping rate gamma 0, and then considers the limit that gamma 0 goes to 0, right?
Right. Yeah, in the superconducting state. Yes.
Okay.
Okay, thank you.
Okay, thanks.
You're welcome. Bye.
Any other question? Another one. Yeah, there is another question from Jonathan Wise. The shape of the heat transmission coefficients had the same shape above and below the critical temperature. What was this expected?
Okay, it's expected because part of the dielectric function is, according to the experiments, is temperature independent, but at low frequency there is a suppression of the low frequency modes, and this is the more important the more important result, because this suppression of low frequency modes cause the 2 order of magnitude decrease of the heat flux. Yeah, it's only in the two fluid models there are two kinds of carriers, normal and condensed, and only the Drude term is affected by this condensation. Mid-infrared and phonons are unchanged in the transition.
Okay, since usually there are not many questions, I'm going to tell you the last one. Okay, George Palasanzas, do you have measured optical data?
Sorry?
He's asking if you have measured the optical data, like the type.
We use previous results of another authors to model the electric function.
Okay.
Yeah.
Okay. Thanks a lot, Shunashi. We need to continue. Very nice talk. And the next speaker is Luis McDowell, and he's an invited speaker. Luis, whenever you want, you can start.
Okay. Hello, everybody. Can you listen to me?
Yes, we can.
Okay, so let me find my talk. Now, there we go. Can you see the screen now?
Yes, also.
Okay, so good morning, everybody. And thank you very much to the organizers for organizing this interesting mini-colloquium on Casimir effect. And particularly, thank you very much for this extra effort that has been required to overcome the difficulties with coronavirus and to keep the conference online. Thank you very much also for providing me the opportunity to describe our recent research on the crossover of London to Casimir interactions. This is work that has been done partly in collaboration with Juan Luengo and some other collaborators that I will acknowledge at the end of the talk. So, of course, everybody here is familiar with Casimir interactions, but actually, perhaps because you are such specialists, you might not be aware that there is a very large community of chemical physics which never in his life has heard about Casimir interactions. Or if they have, they believe it's really an exotic effect that often can be ignored. So chemical physicists typically what study is that from quantum perturbation theory, you can find that atoms interact in a pairwise additive fashion through a London potential. And if then you are concerned with many atoms, such as shown in this cartoon, where you have two macroscopic plates separated by a distance d, then you can add up all of these London interactions into free energy as a function of plate separation, which has the usual Hamaker dependence, in which the energy decays as the inverse power of d, second inverse power, and a coefficient which is the Hamaker constant. But of course, we understand that when the distance is large enough, then the London potential turns into a Casimir polar potential, and the decay of the intermolecular interactions becomes faster. And this that occurs actually between pairs of atoms can also be, has also say a signature in macroscopic bodies, where typically it implies that the well-known Hamaker behavior crossovers into the Casimir behavior. Okay, and of course people are familiar with the Hamaker limit and the Casimir limit, and this Casimir limit for plates is what actually allows one to measure intermolecular forces experimentally, at least in the early times, and it is the way that people find manifestations of the Casimir effect. But so we are familiar with these two limits, but actually how is the crossover between both these limits as you go from d to the power of 2 to d of the power of 3 is much less known, and chemical physics don't even typically know that this occurs at all. But why not? Because these forces are usually very small in the chemical sense. But when you're interested in systems like the adsorption of water on a substrate, the water films can become very large, and then they do no longer feel this Hamaker form, but actually they feel the Casimir form. So it is also interesting in chemical physics systems, but particularly because the crossover from the Hamaker regime to the Casimir regime often is accompanied with a sign reversal of the Hamaker constant, okay, of the effective Hamaker constant. And so then, even if the effect is very weak, it has dramatic consequences. So because you go from repulsion to attraction or vice versa, okay? So of course, this crossover is well known for a long time in some sense, and the sense is shown here in this horrible slide. From now on, I will, rather than talk about interaction energies, I will talk rather of Hamaker functions, okay, because they convey all of the information of the free energy, but in a domain of orders of magnitude much more manageable than the free energy, okay? And then we can use DLP theory to obtain that Hamaker function. Since DLP, we know actually that Hamaker is not a constant, it's a function. And it is given here, it has this horrible form, but the important point is essentially that you can calculate it very accurately, provided you know your dielectric response of the system for a given number of frequencies, these frequencies which are known as the much better frequencies, and which span all of the electromagnetic spectrum. So the important point is that even though we have a theory, and the theory is known for a long time for experts, this theory cannot possibly go through a large community of chemical physicists, mainly because it's really one equation that is only useful for numerical calculations. You can hardly make any easy interpretation of this result. So the main goal of this talk is to find working equations that will allow us to describe the Hamaker function for all the regime of plate separation. And the only way you can do that is by adopting a strategy that is somewhat different than the usual strategy in theoretical physics, because in theoretical physics, typically you like to do, you do perturbation expansions, which are systematic and exact within a limited range of the parameter space, and then break down completely. So what I will do rather is to find an approximate expression, which is always approximate, is not systematic, but that will remain robust and convey all of the information of this result for all plate separations. Okay, so of course I need to do some simplifications, and the most useful simplification to deal with this Hamaker function, at least in the Hamaker constant limit, is to linearize this logarithm. And so then I get this equation, which is actually much nicer. Already the linearization gives us some much nicer equation. And one point that I would like to make is that this linearization is really robust. In my experience, you lose the exact result, obviously, but you never lose the right physics. So it is a very robust approximation. And the main important point here in terms of analyticity is that now here, you can recognize this as a distribution. So if this is a distribution, then these functions, which I will lump into R, the dielectric function, this is the function that conveys all of the material properties in the system, then can be factored out of the integral using the mean value theorem. And then we are left with really a trivial integral. And of course, let me point out that this sum, it is very important to split it into two contributions. This is really important at finite temperature, where experiments are actually carried out. So I split the sum into a zero frequency term, whose result is well known, and a high frequency term, which conveys the non-trivial part of the problem. And of course, this is just a formal manipulation because we do not know what the value of mean X star is. And as long as you don't know it, then this is just a formal statement. So what I do here is a trick that is inspired from actually a numerical method. The calculation of integrals is very useful to do Gaussian quadrature rules as a well-known numerical tool. But typically you use the 2-point, 3-point, 4-point Gaussian quadrature rule, and you have a numerical method. The idea here is to use a 1-point Gaussian quadrature rule, not as a numerical method, but as an analytical tool. So the idea is that I want to find a mean value of this integral, so I can factor out f, but I don't know what the mean value of x is to value that function. So I assume that f is the most simple possible function that I could think, just a linear function of x. And then in that case, I can get a very simple rule to find the value at which I must value my function f. And because my weight here is really a trivial weight, these integrals can be solved analytically, and I get a prescription for the mean value of x, which, as you can see, is a function of the distance between the plates. And this is just a 1-point quadrature rule. Okay, so, okay, how good is this? We checked that the approximation is really extremely good and surprisingly good for rather difficult situations. Here I am plotting Hamaker functions calculated exactly with the Lifshitz theory, shown in black, compared with this Gaussian quadrature approximation shown in red for a number of different systems, which show a very exotic Hamaker function, that is non-monotonous. Okay, and you see that even for these rather demanding systems, the approximation never is exact, but is always qualitatively correct. So one is encouraged with this approximation, and so we would like perhaps to try to push further our analytic treatment. And so we have this sum which cannot be evaluated exactly. So now we do a rather standard trick, is that we map the summation index into a new variable. This is a much better wave number. Okay, I'm mapping into wave numbers, which allow me to set the scale of plate separations very, very intuitively. And then I can find that the increments of the summation index map out into increments which are infinitesimally small for most temperatures. So then I am allowed, even at finite temperature, to convert my sum into an integral. But the very important point is that because I have split the Hamaker constant into zero frequency mode and large frequency mode, now I have a lower bound of my integral, which is finite. And this is a very important issue that will convey information on the crossover regime. Typically, this continuum approximation is performed for the zero temperature limit, and then the lower bound is zero. But putting here a finite bound is very important, as we will see later on. Okay, so I have now my continuum limit, so a nice integral, but still this is a rather tricky integral because the way it converges, it's very tricky. I need the integral to converge, of course, but it converges for very different reasons depending on what value of the plate separation you have. Okay, in the limit of small d, then the exponential function is constant. It's not a it's not a well-behaved distribution, and the convergence actually is dictated by the dielectric function. And then I get the Hamaker limit. But if, on the other hand, d goes to infinity, then my dielectric function remains smooth, and the convergence is actually dictated by the exponential function. So in that limit, I get clearly recognizable here the Casimir regime. Okay, but the problem is that I cannot use in a simple way the mean value theorem to evaluate this integral, because for small d, the convergence is dictated by this distribution, while for large d, the convergence is dictated by this distribution. So I cannot find a simple prescription, a mean value theorem that will remain correct at all distances. So what I do here is to use a trick that is typical for practitioners of Monte Carlo simulations. Okay, I have my integrand, it's here, and now I am going to multiply my integrand by this exponential function. And this exponential function is meant to mimic the decay of the dielectric function. So you need to put here a parameter nu infinity, which dictates the range of frequencies in which the dielectric function starts to decay. Okay, for the time being, it's just a parameter. Of course, I need to I need to have this integrand be exact, so I'm multiplying by this other term such that actually I have just multiplied by 1. And with this trick, the important thing is that in the square brackets, now I have a simple exponential function that has all of the convergence properties of the real integral. It will converge both at 0 distance and at infinite distance. So I can now apply the mean value theorem to this part of the integrand and factor it out. And then I am left with a trivial integral. So I just calculate the integral and get my full prescription for the Hamaker function as a function of plate separation that is good from 0 plate separation to infinity. Okay, and of course, because I have used the mean value theorem, I need to know at which mean frequency or mean wave number do I need to evaluate my dielectric properties. But I use again this Gaussian quadrature trick, and I find a somewhat clumsy but a simple algebraic expression for the frequency. And one can check readily from this expression that the dielectric properties are to be evaluated at high frequency for small distances and at the thermal Max-Weber frequency for large distances. Okay, so once I have this expression, I can readily, without any not profound knowledge on quantum theory and quantum relativistic theory and field theory, I can interpret all of the results conveyed to us by Lifshitz. And some of us are happy to use it without really understanding a word of what Lifshitz did, actually, I must say. So at small distances, we indeed find the Hamaker limit, in which the Hamaker function is just a constant, and the dielectric properties are evaluated at high frequencies. Then there is a region between the excitation wavelength and the thermal Max-Weber wavelength, in which I recover the the Casimir regime, and where the dielectric functions are evaluated at frequencies in between the thermal and the excitation frequencies. But, and perhaps this is not that widely recognized, at sufficiently large distances beyond the thermal wavelength, then this Casimir effect is altogether suppressed exponentially, okay? And of course, if we are at 0 temperature, as Casimir did his calculations, then this wave number is 0, and we get through all of the D regime the Casimir effect. But at finite temperature, this is actually not the case. So at temperatures where experiments likely can be measured, for example, at 300 Kelvin, this Max-Weber wavelength is about 4 micrometers, which is, I believe, about in the limit where experimental measurements can be performed. Okay, so if the plate separation is smaller than this Max-Weber thermal wavelength, then indeed I have the Casimir behavior for the free energy. And notice, however, that by use of my quadrature, I am introducing finite conductivity and finite temperature corrections to the Casimir result. And as you can see here, the dielectric functions are to be evaluated at a frequency which depends both on temperature and distance. And so this shows that corrections to the Casimir effect are actually entangled. Both temperature and finite temperature, and finite conductivity effects are entangled and cannot be separated. Eventually, if the distance is larger than the much better wavelength, then I get indeed the exponential suppression. Okay? So that's as far as the qualitative study is referred to, but for chemical physics applications, one would also like to use this method as a method for calculating Hamaker functions in an easy manner. So what I do now is to notice that in the limit of 0 plate separation, I have an simple analytical expression for the Hamaker function, which is a function of this parameter that I have introduced, which is not defined yet. So what I do is simply to map this result into some well-known formula for the Hamaker constant. For many materials, it is sufficient to describe their dielectric response with just one single Lorentzian oscillator, and in that case, you can obtain a Taber-Winterton closed expression for the Hamaker constant. I just map these two expressions, and I get an analytic result for my new infinity parameter, which is just a function of the refraction index of the material and the excitation frequency. Okay, so with this, I can now check how good my formula is. And here in this slide, I am showing mica, 2 plates of mica separated by vacuum, and the red symbols that you can see here are exact results from Lifshitz theory, while the orange line is my weighted quadrature approximation with no parameters whatsoever. Okay, I can tweak a little bit more my approximation by noticing that this new infinity actually should be a function of plate separation, and then suggesting this heuristic formula and then just one single parameter which is not material dependent, I get this blue line, which is almost exactly describing my numerical calculations. The point that I would like to make is that at finite temperature, the exponent of the energy never really reaches the limiting value of 3. Here I am plotting the effective exponent from 2, which is Hamaker, to 3, which is Casimir, and really you never reach the N3. At about 100 nanometers, you are already decaying, and you go back into N2, which corresponds to the contribution of the 0 frequency mode of the Hamaker function. Okay, still, for some people, the expression that I obtained might be just too complicated, and then there is a theorem which is perhaps not well known, which has been really powerful for me, because we have this limiting the continuum approximation, and actually because R, the dielectric function, usually is a monotonous function, you can apply what is known as the second mean value theorem, which allows us to factor out R, evaluate R at the lower bound of the integral, provided you introduce into the integral a cutoff of the bound. And this physically, I think, is really appealing, because when one does numerical calculations, one has concerns about how far d should become small and how far the frequency should go to infinity. And what this theorem shows is that there is a natural cutoff frequency in the Lifshitz formula. Okay, and then this can be integrated trivially, and you obtain this very much simpler expression, which also conveys qualitatively all of the information of the Hamaker function. Okay, we can do the same trick as before. We just match my new expression for the Hamaker function to the Hamaker constant obtained from Taber-Winterton. And what I obtain is a simple expression, which is just a function of refraction indexes and excitation energy. So it requires just the same information that people in the colloidal community use to calculate Hamaker constants, but it provides the full Hamaker function. And here I show the comparison between exact Lifshitz results and this frequency cutoff approximation for two different systems. And as you can see, the formula is really very robust. Okay, so you can claim that in some situations, the dielectric function R is actually non-monotonous, so you cannot apply this approximation. Okay, for example, it has been suggested that ice, water, air is a case where this dielectric function is non-monotonous because you have a crossover from a region of low frequencies where the dielectric function of water is large to a region of high frequencies where the dielectric function of ice is larger than that of water, and then R becomes non-monotonous. But in that case, you just need to split this integral into different intervals in which R remains monotonous, and then you apply first mean value theorem to the first integral, you apply the second mean value theorem to the second integral, and then you get, well, a somewhat lengthy expression, but that can be interpreted easily. Yeah. And indeed, you can confirm that there is a crossover, a sign reversal of the sign of the Hamaker function. So within the Casimir regime that can be identified here, you have a small distance regime where Hamaker function is negative, and still within the Casimir regime, eventually it becomes positive. In one case, the Hamaker function is dominated by dielectric response at ultraviolet frequencies, and in the other, it is dominated by dielectric response at infrared frequencies. Unfortunately, it has been shown by Fiedler, and there will be a talk in a while on that this parametrization of ice and water that have been performed by Elbaum and Schick is not accurate. So actually, this crossover does not happen in this system, but it does apparently happen in some other systems, which I have checked here. So it was suggested that a sign reversal can be found in this well-known system of gold and silicon oxide in bromobenzene, but the crossover occurs only at 3 nanometers, and so it can hardly be measured experimentally. We have studied a number of systems in which we find that there is sign reversal of the Hamaker constant here and also here that occurs at about 100 nanometers. So for these systems, I suggest it's perhaps experimentally interesting to study where we can check a sign reversal of the Hamaker function. So we're not really concerned whether it is positive or negative. Actually, it can be both for the same system. And perhaps this system here, which is made just of solid substrates, solid plates, would be a good candidate for experimental verification. Okay, so let me now go fast with the 4-layered media. How minutes have I left? Sorry?
7 minutes, sorry.
7 minutes, okay, then I'm well in time. So now I want to extend these ideas to 4-layered media. Okay, 4-layered media have been studied many times because often you have a metallic plate, and metallic plates are never pure, and you have an oxide layer or some inert layer, and so you need to account for the dependence of this layer, say layer 3, not as a result of interactions with this semi-infinite medium, but also across the inert oxide layer, and then the formula have been worked out for that case. Actually, we're interested in a different system because we are interested on how ice adsorbs onto some materials, which could be nucleating agents, and so are in the presence of an infinite amount of air. And in that situation, ice could partially melt and have also a water layer. But these are not inert layers. They feed one from the other. So both L and D are variables here. And surprisingly, the Lifshitz formula for this system had not been worked out previously, it seems. But actually, you have a form of the Lifshitz formula which is very general for whatever media you use, where the free energy is given as a function of the dispersion relation of the media. So you just need to plug in the correct dispersion relation, and we worked out the dispersion relation of the system, which is shown here and published recently. And it is a very appealing formula because it shows that if D goes to infinity, then you'd have ice sandwiched between silver iodide and water, and this term would vanish and this term would vanish. You'd be left just with the dispersion relation that is familiar for three-layered media. So actually this dispersion relation contains information on several permutations of the layered systems, and it's very powerful. So if we make a linearization as we did before, then you can actually show that this potential, which is a two-variable function of the four media, can be split into simpler functions in which you can recognize the free energies of three-layered media plus a correction. And this correction is what messes up things, because it's a function of two variables, and really screening over two variables for free energies that span 20 orders of magnitude really is not nice. So what we notice here in our system is that the two layers have very similar dielectric functions, because it's size and water, both very similar. And so under that approximation, it can be shown systematically that this function of two variables actually becomes the sum of three functions of one single variable, which is very convenient. And doing the same tricks I have been showing for three-layered media, actually you find that each of these three functions has exactly the same functional form. We recover dependence of L that is given by the weighted quadrature approximation that I showed before, and only that the media, the energy between 1 to 3 layers is given by the thickness of layer 2, and then the other one is given by the thickness of layer 3, and then the correction is given by the sum of the thicknesses of the two layers. And this simplifies very much calculations, and hopefully will allow us to also make some interesting qualitative statements about interactions. For the time being, let me just show work and progress, where I show here the free energy of my four-layer system as a function of D and L, the two water and ice separations. And this is calculated here exactly using Lifshitz formula, and using the expansion that I have shown here, then you get this other result, which, as you can see, qualitatively is just the same, and you can check numerically that it's really, really very accurate. So in essence, very complicated calculations of this function can be transformed into simpler calculations of which are the sum of one single variable functions. And these three functions can then be made analytic through approximations shown previously. So let me just go to my conclusions. That I hope I have shown you that we have now a simple formula that are really well behaved and depend only on parameters of the system and not empirical parameters, which allow us to describe the crossover from London to Casimir regimes, and also allow to stress the suppression of Casimir interactions for sufficiently large plate separation. The equations that I have shown do not require any further input that it is required to calculate Hamaker constants in the colloidal community. Then I also have shown that it is quite common to see a sign reversal of Casimir forces, of Hamaker functions in the Casimir regime. And I have shown some candidates in which such effect could be measured, and particularly for AFM techniques, perhaps this system in which both limiting media are solids could be an interesting test system. And finally, as a very general remark, I would like to stress that Gaussian quadrature rules, one-point Gaussian quadrature rules, appear to be really a very powerful analytical tool in physics, provided you find the correct behavior of the weight function, as I have shown here in this talk. And then finally, let me thank my research team, my modest research team, Juan Lengo, who's doing a master thesis, Fernando Izquierdo Ruiz, which was a postdoc, which disappeared with his results, and then my collaborators in the last year. So thank you very much for your attention, and I'll be happy to take any question.
Okay, thanks, Luis, for your very nice talk. Is there any question? Not yet in the chat, despite I asked them to do that. well, in the meantime, I have a question. So the approximations are really nice. They are really excellent. I liked it very much. But at the same time, when you showed the first figure, when you show how good your approximation was compared to Lifshitz theory in the Mika system, you also showed the experiments, yeah, here. So I understand that your aim is to try to mimic Lifshitz theory, but you consider to try to tune your parameters somehow to try to understand what's going on in the experiment and conclude something from your theory.
Okay, so I used this system because I thought it was really a paradigmatical system, but to my surprise, there aren't that many experimental measurements for this system. I only found 2, and the ones I'm showing here are from historical experiment of Tabor and Israelishvili. Okay, and what it has been found later on in papers by Ninham and Richmond is that actually these experiments suffered from one small systematic error, which is that the radius of the tip was wrong by a factor of 2. So the experimental results are not correct. But I would like to point out something also that I skipped, is that I believe that the authors of these experiments were biased by the known limiting behaviors, which is the, Hamaker to Casimir behavior, which is the well-known, and what experimentally they were tempted to interpret that their, exponent, their experimental exponent, crossed over exactly from 2 to 3. And I think that likely was some experimental bias, because what we find is definitely that at finite temperature, you do never really reach exponent of 3.
Okay.
It starts decaying. So I started doing this work and was looking forward to have a nice comparison with this historic experiment, but then I believe it suffered from some problems, even though it's still very valuable as a pioneering work.
Thanks. There is another question from Kimball Milton. Maybe you can also read it with, I will read it loudly, but maybe it's easier for you to read it yourself. So replacing Matsubara's sum by integral involves Euler-Maclaurin corrections. Are those corrections included or relevant?
Yes, that's a good point. I have included my Euler-Maclaurin corrections, and they do not modify any of the results until the distance is as large as the thermal wavelength. Okay, so I think I didn't introduce my Euler-Maclaurin corrections here just not to mess up too much in the talk, but in the paper I have added them. And the good news is that for the frequency cutoff approximation, the first Euler-Maclaurin correction just changes a factor here. So it does not add any analytical complexity into the problem, which is very convenient.
Okay, thanks. Any other question? Thanks, Kimball said. It seems no. So then, thank you again, Luis, for your nice talk. And we will continue. Of course, to all of you, I just want to remind you that the session will be open until 1:30 again. So in case someone wants to contact somebody else, you will have some time afterwards, as in our coffee break, let's say. So let's continue. Next speaker is Nicolas Chevrolet. We need you, so, okay, so now we have we can see it already. But we cannot hear you. No. Sorry, Nicola, but we don't hear you.
Yes, it should be okay.
Now. Okay, now, okay.
Okay, so thank you, Sol. So first of all, let me join with the previous speakers to thank the organizers for this beautiful colloquium. So it's especially interesting for me, as I'm not quite an expert of these topics, So I can really learn many things with this type of event. So thank you again. So in this presentation, I will try to explain how the propagation of light in certain nonlinear media naturally gives rise to long-range coherence that actually looks very much like the one you usually observe in the so-called quasi-condensates in the context of quantum gases, ultra-cold quantum gases. And I also show that this phenomenon can be used, at least in principle, to generate sizable Casimir-like forces. So the general context of the talk are the fluctuation-induced forces. So of course, the historical example is the Casimir effect, which is triggered by quantum fluctuations of the electromagnetic field. But as we have seen, for example, yesterday, you may also observe Casimir-like forces in other configurations. So for example, in the vicinity of the critical point, in binary mixtures where you have stronger fluctuations, strong thermal density fluctuations, this is the critical Casimir effect. And actually, if you even take a broader view, you may, in principle, measure Casimir-like effects in any configuration where you have fluctuations with long-range correlations. So that's the case, for instance, in liquid crystals, in superfluid helium films, and also in one-dimensional superfluids, which are usually realized in labs using ultra-cold atoms. But of course, this doesn't mean that it's easy to measure directly a force in these setups. So this is the configuration we have explored. So actually, it's a completely classical optical configuration where you have here on the left side just a monochromatic laser beam, which is coming from the left. And this laser is supposed to be weakly incoherent in the sense that it carries shallow spatial fluctuations. And the reason why we take such an initial state will be clearer later. This beam is impinging on the nonlinear Chi3 medium, which lies on the side of the positive Z. So with this configuration, I will address three main questions. The first one is how do these initial fluctuations evolve during the propagation in the Kerr medium? The second question is what type of Casimir-like force do you get if, for example, you place here two objects, like two plates are in the nonlinear material? And third question is is this force universal, or perhaps more modestly, to which extent does this force depend on the microscopy of this setup, and in particular on the statistics of the fluctuations? So before getting into the matter, let me forget the plates for a moment and just recall how the propagation of light is usually modeled in nonlinear media. So the first stage is to express the electric field as follows. So this is just a monochromatic plane wave weighted by a spatial envelope. Then you insert this expression into the wave equation together with the formulation of the permittivity of the Kerr medium. So you have this nonlinear term here, which depends on the time average local intensity. And then you make the assumption that this nonlinear term is small, and also that typically the envelope of the field varies weakly at the scale of the wavelength. So this leads to this so-called nonlinear paraxial wave equation. And the interesting point here is that this is exactly the same equation that you also have in the context of quantum gases for describing the time evolution of ultra-cold interacting bosons. So for interacting bosons, this Z here would be the real time. The wave number here would be just the mass of the particles, and this nonlinear term just would be due to the contact interactions between the particle. And that's the reason why due to this analysis, and here the terminology fluid of light to refer to this classical optical setup. Okay, so the goal here is to model the propagation of a weakly incoherent beam inside the nonlinear material. So as a simple model, we take for the initial envelope at z equals 0 here, just a simple superposition of a perfect plane wave of intensity I0 and the shallow part here that fluctuates randomly in space. And for it, we just take a speckle model. So phi here is just a random Gaussian variable with a certain correlation function, gamma, and this gamma decays over a certain correlation length, sigma. That's the correlation length of the initial speckle. And then we describe the propagation of fluctuations in the medium by looking at the coherence function, the so-called G1 function. So this function is plotted here as a function of the separation between 2 points in the transverse plane at increasing value of z. So that's obtained from a numerical simulation of the nonlinear Schrödinger equation. So at 0, z, of course, G1 is very close to 1 because you start from something which is almost like a plane wave. The initial fluctuations are small. But what you can see here is that very quickly, these fluctuations are amplified by the nonlinear medium, and this comes together with the spontaneous emergence of a long-range coherence. Yeah. So to explain these results, we have used a theoretical approach which is inspired actually of the physics of quantum gases. So it's called the Bogolyubov theory. So we have actually extended it to this problem of classical optics. So it works as follows. You express here the field envelope in an intensity phase representation where I and theta are random variables here. And then you use that the initial fluctuations are small to linearize with respect to the intensity fluctuations. On the other hand, you do not say anything about the phase fluctuations. So if you do so, you obtain these Bogolyubov-de Gennes equations. And the remarkable property of these equations is that the phase fluctuations averaged over the statistics of the initial speckle growth logarithmically with space. And this logarithmic growth is a peculiarity of two-dimensional fluctuating systems. So actually it's a consequence of a much more general theorem of statistical physics, which is the Mermin-Wagner theorem. So this theorem essentially states that in any low-dimensional system, even tiny fluctuations break any long-range order. And in particular, it explains why, for example, you cannot have stable crystals in 2 dimensions in the thermodynamic limit. So this is exactly what we have here. And for our purpose, the practical consequence of this logarithmic growth of the phase fluctuation is that the G1 function decays algebraically with space at sufficiently long distances z. And this is exactly what we observe in the numerics. And there's also another prediction of the theory, which is that this result is actually to a large extent completely independent of the shape of the initial spectrum of the fluctuations. So in fact, the exponent alpha here of G1 only depends on a small set of parameters. So you have epsilon here, the amplitude of initial fluctuations. You have psi, the Healing length, which is a characteristic length of the nonlinear medium. And you have sigma here, which is just the second moment of gamma. But you can change the shape of gamma and the result typically will not be modified. So in other words, we have here a system which is very simple, where you start from initial short range and non-universal fluctuations, and they are naturally converted into long range and to a broad extent universal fluctuations. Incidentally, this is exactly what is also found for 2-dimensional interacting quantum gases, which form in 2 dimensions so-called quasi-condensates. And these quasi-condensates, they have exactly this correlation function. Okay, so now that I have described the propagation in the bulk medium, let me add these two plates and compute the Casimir-like force between them. So to do this, we have used...
5 minutes left.
Yes, thank you. So to do this, we have used a version of the scattering approach to Casimir forces, which was developed in the early 90s by Jekyll and Reynaud. The main assumption we have made here is to neglect the boundary effect near z equals 0, and in particular the fact that here the light may in principle be scattered on the side of these plates. So we have neglected this effect. In a nutshell, this is how this approach works. First, you compute all the fields inside the three regions by using the reflection and transmission properties of these plates, and in particular the unitary of the S matrix. Then you compute the pressures in the three regions using, for example, the stress tensor of the nonlinear beam, which was, for example, derived in this paper. And then you average over the fluctuations of the initial state. And finally, you compute the Casimir pressure as a difference between the pressures on either side of the plates. So this is the final result. And in a way, it has the very same structure as the usual Casimir effect in vacuum. So here the pressure is governed by the spectrum of spatial fluctuations in the absence of plates, weighted by the kinetic energy of the paraxial photons along a direction which is perpendicular to the plane of the plates, and also by the spectrum of the cavity here, and the pressure follows by integrating over all possible momenta. In fact, this equation can be further simplified if you remember that in the paraxial regime, the angles of incidence are typically large, which means that the reflection coefficients are very close to 1. So it's a bit the same as in the perfect mirror. And then you can compute this integration of a Q perp, and you get this simple formula where the pressure is just a sum over a second derivative of G1 evaluated at the spatial modes of the cavity. So in other words, here the pressure is just controlled by the coherence of the beam in the absence of plates. So this is the pressure shown as a function of the plate separation. We have identified here two well-distinct regimes. The most interesting one is the regime of large plate separations, where the force is attractive. It decays algebraically, and this decay is rather universal according to what I said before. We have also identified here a region where the Casimir pressure is repulsive. So however, it should be noted that here the results depend significantly on the spectrum of the initial fluctuation. They are actually completely non-universal, and presumably here you start to depend very much on the specific details of your setup. So at that point, the natural question you may ask is whether we have gained something here as compared to using, for example, a full speckle from the start. In fact, yes, we have gained something, and we have gained something not only in terms of spatial range of the Casimir force, but we have also gained something in terms of absolute amplitude. Because here we start from small fluctuations, but as I said before, these fluctuations are amplified by the material, and they are amplified in such a way that the pressure you would get from just a speckle here is much smaller than what you achieve with this configuration. So the take-home message is that it's much better to let a nonlinear medium amplify small fluctuations than using large fluctuations from the start. So this is my conclusion. I've showed you that weakly incoherent beams spontaneously emerge, amplify long-range correlations in chi3 medium. And these correlations mediate controllable Casimir-like forces. So they are controllable in the sense that you can, for example, just change the light intensity or the amplitude of the nonlinearity. So there's, of course, not yet experiment for this type of setup, but I'd like to point out that in this recent work, they were able to measure in the very same configuration, the radiation pressure on a single plate as a function of the angle. So this is probably encouraging. And this is just a slide showing the people involved. So this work was done with Tamara, our PhD student, Simon Pigeon, our postdoc. And I would like to thank many discussions with our colleagues and friends, Serge Reynaud and Romain Guéraud. So this is our group in Paris. So don't hesitate to consult our website if you're interested. Thank you very much.
Thanks, Nicolas, for your talk. Let's see if there are any questions. Not yet in the chat. So I have a question. So it seems that you are not really using, correct me, that you don't make use of the curve part of your material. So does this apply to any other nonlinear material? Any kind, or
yes,
because
yes.
the curve part, where is it
Yes,
in
yes.
the end?
So it's, yeah, thank you for this question. So it comes into play in the linearization procedure here.
Okay.
So if you change the exponent, for example, here of this nonlinear term, the full procedure here at this stage will be different. And but I'm not able to say how this result will transform in for other types of nonlinearity. But the argument here is that for any type of nonlinearity, usually you can always, the nonlinearity is always small, and then you can restrict yourself to the second order correction.
Okay, thanks. George says, excellent work, Nicolas. But I don't see any other question. Let's wait a bit because we still have some here. So Victoria is asking, if I understood well, between two equal plates, you find repulsive forces at short separation distances. Would you also find different behavior for these similar materials?
For what type of materials? Sorry.
Dissimilar, so that they are not the same materials, no?
You mean between these two regions? So this is all for the same material. So it's just a generic chi3 medium. And this is just at short distance and that you are repulsive, and at large distance you are attractive. But it's all for the same medium.
Sorry. I prefer to talk about the microphone. No, I was asking if you put two different metals, or even if you put three materials that fulfill the inequation of Salosinski, that says that if the dielectric function of one material is below than the material that is mediating the interaction, and at the same time the other material has a lower dielectric function, then you find a repulsive force. So in that case, you are going to also find a different behavior as you find in this unexpected between two metals that are equal?
Well, no, because here the permittivity I'm talking about is not the permittivity of the object. It's the permittivity of the nonlinear material which lies in between and outside some of the object.
Okay.
So here, I did not say anything about the permittivity of the plates themselves, because in this paraxial regime, actually the R coefficients are typically close to 1, whatever the microscopic details of the plates. Of course, you can also do something more sophisticated, but I don't think it will change this attractive character.
Thank you very much.
You're welcome.
Okay, thanks, Nicolas. There are no more questions. I would like to let you know that the organizers asked us to maybe take a picture, not at the very end of the session. So after the next speaker, if you want, you can switch on your cameras and then we will get a picture of this session today. like a souvenir or so. And so get ready for it after Sara speaks, okay? So next speaker is Sara Babamadi. She's an invited speaker. And so whenever you want, you can start.
Yes, all right. Okay. And then, all right, thank you for the introduction. And also I would like to thank the organizers for giving me this opportunity to have a talk here. And I would like to talk about the Casimir force measurements in complex systems. So I will start my talk with a general introduction of how important it is to measure this force experimentally, and then I will go on with explaining about our method and the setup that we have. And then my presentation will be divided into two main parts. The first part is about silicon carbide, and then results and discussions of this material. And then I will go to the bismuth selenide, the other sample that we had, which is a topological insulator. And we will see the challenges and the results and discussions of this material. So I'm going to start with stating some obvious facts for this audience about quantum mechanics, which says that two metallic plates attract each other even if there is no charge involved. And this effect would be very large when the separation between the plates is very small. In fact, Casimir effect is a macroscopic manifestation of what is known as quantum fluctuation of the vacuum. And again, quantum mechanics tells us that there is no real vacuum, and even in a perfect vacuum, we still have a constant activity of fields, and this field, which is called vacuum fluctuations, and it causes these two plates to attract each other. In fact, in between two plates, you cannot just have any wavelength of the electromagnetic field to put in. The electromagnetic field that quantum mechanics allows you to have in between two plates must have an integer multiple of the half of the wavelength of the electromagnetic field. Whereas from the outside, any wave could be allowed. So the net result is in a way that we have the force, which tends to push these plates towards each other. And it's called Casimir force, and it's basically the macroscopic manifestation of the quantization of the field between two plates. And it can be very strong in short separations. And the interesting thing about it is that it's really dependent on the separation between the two bodies. So this fundamental quantum mechanical force basically limits how we can miniaturize and engineer nano devices, very small switches, for instance. But there's a bigger picture behind this. We are talking about surface science, because when the surface to volume ratio is increasing with the system of the size decreasing, then we have to have as much as possible knowledge about the surface of the interacting bodies. So it's very important for us. And also there has been always a much more theoretical work in this field than experimental. So there has been always a need to probe and measure this force experimentally. And I would say that in theory, even if something is possible and a problem is solvable, which is a big if most of the times, there is a big chance that it doesn't work out in practice because of all the parameters involved, and it just makes the problem even more complicated. So to measure pure Casimir force, we have to take into account different aspects that they are very important, like the electrostatics that they are involved in the measurements of this force, and also the roughness of the interacting bodies, because they will define, the roughness actually define the shortest separations we can have between the two interacting bodies. So measuring the force in plate-plate geometry, it has its own difficulty because of parallelism. And to avoid this issue, we can measure the force in a sphere-plate geometry, which is a very well-known geometry between the scientists. And here you see the SEM images of the probe that we made by attaching a sphere, a micro-sized sphere at the end of a cantilever, a tipless cantilever. And we also measure the force with AFM in contact mode. And you see that it is in a glass jar because we prefer to do it in nitrogen atmosphere to minimize the effect of humidity as much as possible. As I said, we can measure the force in a sphere plate geometry by using PFA, or proximity force approximation, which is a valid approximation when the curvature of the bodies is much bigger than the separation between them. And this condition is fulfilled for our setup because the radius of the sphere that we use is 10 micrometers, so it's big enough. And we use the AFM in contact mode to measure the force, and it gives us the force versus distance curves. Measuring the force during these measurements, a cantilever having a spring constant of K bends over under the load of the force that it feels, and it actually as a consequence of Hooke's law. And it obeys this law as long as the bending is much smaller than the length of the lever. So here we can plot the deflection of the cantilever versus the piezo displacement, basically. So here the horizontal axis is actually the vertical movement by the sample stage, and the vertical axis, it shows the cantilever, the deflection of the cantilever when it is approaching to the surface, touches the surface, and then pushes against the surface, and then goes away from the surface. So it can basically feel the force. So why silicon carbide? Because silicon carbide, as you know, is a very much studied material. It has been used in industry for many years. And it's actually, because of its excellent properties, it's very difficult to be replaced in industry. Because it shows a strong number of, a huge number of polytypes. It has a low residual stress level, and it has high stiffness, and much more. And it was actually studied before in our group, this sample, but our focus was on the different phases of silicon carbide. And we also bring ruthenium into the game because just we wanted to have a metallic reference of like how a metal would behave in our setup. So on the left side, you see, you see the figure of the optical properties that we measured with ellipsometry for the different phases of silicon carbide and ruthenium. And you see that there is a very tiny difference in the optical properties that we measured. Because you know that according to Lifshitz theory, the Casimir force is expressed by the actual optical properties of the materials, right? So we measured the opticals, but we didn't see any difference, any considerable difference between these two surfaces. All right, as I said, we already we did this study before on the silicon phase of the silicon carbide, and there was a very good agreement with the theoretical prediction. But the point here is that this difference, this negligible difference, there was basically no difference in the calculated force. We saw the difference in electrostatics that I will go in the further slides. But first, let me talk about the roughness of the surfaces involved, because it's an inevitable problem when you are measuring with real practical materials. And a very small amount of roughness can end up in a very big errors in the calculated force, in the measured force. So you see here there are samples which were relatively smooth, and the highest contribution for the roughness is coming actually from the sphere that we used. So because of technical issues, we couldn't get a smoother sphere here, and we could image the topography of the sphere by using reverse AFM. In reverse AFM, actually, the role of the tip and sample is inverted. So a sphere is scanned on top of a grid with so many sharp tips. So that's how we could get the knowledge of this, the roughness. And it turned out that we could not get closer than 30 nanometers. I mean, the shortest separations we could have was 30 nanometers. This is the limiting factor, which is coming from the roughness effect. So as I said, we saw a huge difference in electrostatic behavior of the two different phases of silicon carbide. Whereas in the optical properties, we did not see any difference. And the electrostatic calibration is very important for Casimir force measurements, just to minimize the contribution of the electrostatics, and also it can give us a better understanding of the spring constant of the cantilever, and also the actual separation between them by fitting the curves with these equations that we have. And we can assign the minimum of these curves as the contact potential of the system. And contact potential is always exists between two conductive, dissimilar materials that they have been brought into contact with each other. It even exists between two of the same material because they are coming from the different coating process, for example. So you see that in our case, the difference between the contact potential between the two different phases of silicon carbide is dramatically high. It's actually considerable, which basically will end up in the difference of the force that we measured. So, okay, and another thing that I have to say here, that we can relate contact potential to the work function of the system. And the work function actually consists of the two main parts, the bulk contribution and the surface contribution. So for us, the bulk contribution was, of course, the same, and the surface contribution must be different. And so this is because we have a different chemical environment on the different phases of silicon carbide. We have more nitrogen and oxygen on the C phase. We got it from the XPS results, which will cause higher work function, as we saw in the contact potential difference as well. So here you see the final Casimir force measurements that we did for different phases of silicon carbide, the Lifshitz theory calculation, and also on the right side you see the measured data for ruthenium. As you see, the difference is, there is a difference between two phases of silicon carbide. But what is the reason? What is the reason for this, that we cannot see it in the Lifshitz theory? Because in ellipsometry, the penetration depth of the photons that they will give you the average value of the epsilon is much higher than the effective depth of the surface layers for different phases of silicon carbide. So it is basically not sensitive enough to capture this difference, so we could not see any difference in the Lifshitz theory prediction. But we can say that not only the optical properties matters here, but also the conductive state of the surface plays a very important role, and it cannot be neglected. Sorry. Okay. I would say that understanding Casimir force provides this accessibility to the micro and nano size physics. And it's very important to understand it. And we saw different electrostatic behavior of the different phases of silicon carbide, which turned to be very important, and the effect was shown in the measured Casimir force. But it was not shown in the calculate force, as I said before. And roughness is always a limiting factor because it defines the shortest separations we can have. And the previous slide, you see that there is a huge discrepancy between the experiment and the Lipschitz theory for the ruthenium in the shortest separations. And we assume that this effect, the roughness effect, will increase with increasing the metallic behavior of the system. So moving on to the other project, I'm going to just give you a quick review of what a topological insulator is and why there has been an explosion of theoretical and experimental work about these novel materials. Basically, the discovery of topology and the band structure opens the doors for the new advances in solid-state physics, and it's very interesting to understand this topology in a sense that how it manifests itself in the systems, and also how it can provide a platform for new device applications. So topological insulators are actually a class of these materials that they are characterized by having a conductive surface on an insulator bulk. And this surface states on the surface, they are crossing the band gap of the bulk. And these surface states are protected by the time reversal symmetry and the spin orbit coupling, and it cannot be broken. This symmetry and coupling cannot be broken unless we apply a magnetic field. For non-magnetic disorders and perturbations, it can be preserved. So here you see the, yes, and also the other feature that time reversal symmetry and spin orbit coupling brings in these two materials in topological insulators is that the charge carrier densities have a specific spin orientation, which is directly related to the momentum. So it's called spin momentum locking that we have here. And people try to measure the band gap of these materials, but for this material, for this project, we used bismuth selenide, which is a very well-known three-dimensional topological insulator. And the measured band gap for this material, there is a big disagreement of, on what the accurate number is. Okay. So here, a very natural question to ask is how Casimir force or effect would change with using these topological insulators. There has been a huge number of theoretical prediction to predict how Casimir force would change with these systems, and some proposing that they can tune and engineer the Casimir force or effect by using topological insulators. Here I bring the figure that they say that they could have actually get access to the repulsive Casimir force by using two topological insulators, and by tuning the distance between the plates, and also by controlling the topology magnetoelectric polarizability. So to implement these materials in commercial devices, we have to have a better understanding of how they would behave due to the vacuum fluctuations when they are approaching other materials like a metal. So that's what our setup is. It's actually a bismuth selenide and a gold sphere. Right. Here you see the topography image of the bismuth selenide, which is captured by AFM, and you see this triangular features, which is coming from the growing process, and which, they are indicators of the very high quality of bismuth selenide. And on the right side, you see the atomic structure of bismuth selenide, which is a super lattice of 15 atomic layers with repeating quintuples, and which are separated by van der Waals gap. As I said, we need to have the knowledge of the surface as much as possible. So that's why we did XPS measurements on the sample to see what is the chemical environment on the surface of the sample. And our sample were exposed to the air, so they are away from its ideal, perfect, expected topological insulator behavior, but I can say that it's more practical. So we saw that the oxidation happens on the surface of the sample. We had carbon, and the existence of oxygen speaks for the existence of water as well. And we could also measure the work function or the electron affinity of bismuth-selenide with UPS or ultraviolet photoelectron spectroscopy. And it turned out to be 3.4 electron volt, which is lower than what it has been reported in the literatures, but also it has been reported in the other literatures that the work function or the electron affinity would decrease when the sample is exposed to the air. So here you see the electrostatics of bismuth-selenide that we measured over time to see how reproducible and how stable our system is. And so different colors in this figure coming from different time scales. And we saw that the electrostatic response of the system is actually consistent and reproducible over time, and in all the measurements, as I said, I mean, all the measurements are exactly the same as what we did with silicon carbide. So the minimum of this curve actually points the contact potential of the system. And we see that all the curves are merging at the minus 200 millivolts. And it was consistent, so we can say that the contact potential of the system is 200 millivolts. But as I said, there is a connection between work function and contact potential. But just the sole comparison of the work function of a metal and the electron affinity of semiconductor is a very oversimplified picture of what's happening in the reality, because we are basically ignoring what's happening in the interface. The interface here is very important because actually topological insulators are famous for having a very high competition between the surface and the bulk. And these electrostatic variations might come from the Fermi level mediated differences in charge carrier densities between the bulk and the surface. And yes, it's not trivial to just find the semiconductor conductor's electron affinity just by comparing it with the work function of the metal here. But the actual point, the message of this figure was that the applied, I mean, the voltage that we have to apply when measuring Casimir force is minus 200 millivolts. So here you see on the right and the left side the optical properties of our system, and then on the right side you see the Casimir force measurements. And actually I kept the most interesting part for here. We have two different thickness for bismuth-selenide. One is 10 nanometers and the other one is 100 nanometers on top of a substrate, and the substrate is aluminum oxide. And also we approached the calculation from Lifshitz in a double layer system just to take into consideration the effect of, the effect of the substrate. So yes, you see on the right side the calculated force and the measured data for two different thicknesses for bismuth-selenide. And the very interesting thing is happening here, that depending on which thickness we have completely different behavior of the measured Casimir force. It appeared to be that the charge accumulation is very much more pronounced on the thin film of bismuth-selenide, whereas for the 100 nanometer bismuth-selenide, we see reasonable basically agreement with the theoretical prediction. So this is what's happening here. Actually, this study is not complete yet. And I'm going to measure another sample with a thickness between these two samples to see how it differs, and also to have a solid and concrete conclusion of what's going on. So here, any comment, feedback, or idea is very much appreciated. So as the conclusion of the last part, so we see that the topological insulators are emerging, are very important in these emerging nanotechnologies and micro technologies. So it's nice to have a better understanding of how they behave due to the vacuum fluctuation. And we saw that the exposure to the air makes this system behaves as poor conductors, because, as you know, they should have a conductive surface and an insulated bulk, but the behavior that we saw is more like a semiconductor or a poor conductor. So the electrostatic behavior of bismuth selenide was actually very stable over the period of time of 6 months. And all the time it was minus 200 millivolts. But the Casimir force measurements on 2 different thicknesses of bismuth selenide showed that for 10 nanometers, we somehow could not compensate the electrostatic contribution to the force. And there's a big shift between the theoretical prediction and the measured data. And it's a dramatic electrostatic effect. And the last point that I can say here is that the thickness matters in measuring Casimir force for topological insulators. So with that, I would like to thank George, my supervisor, Vitaly for his theoretical input and contribution, and you for your attention. I think I'm done.
Thank you very much, Sarah, for your interesting talk. And now questions are open, so if anyone has any question, please. Okay, we have the first question. I don't know if you can see it, Sarah. I will read it out loud.
No, I cannot.
On the chat on the right, can you see it? No. Maybe if you answer your screen.
All right. Where is the effect of magnetoelectric? No, we didn't measure the.
Excuse me, I'm going to read the question out loud.
Yes.
Have you measured the effect of the magnetoelectric topological coupling as a function of frequency for the topological insulators?
No, we did not measure this. And I don't know how it could affect the Casimir force measurement. But yeah, we did not measure this effect. And actually, I'm very new to this topological insulator field, so there might be some reasons that I don't know.
He says that this is the source of repulsion between topological insulators when it was proposed.
All right. Okay. No, we did not measure the effect.
Any other question? Yes, there is another one from Louis McDowell. Were the optical properties measured experimentally or quantum mechanically?
It was measured experimentally with ellipsometry measurements, so it was experimental work. Was it the answer? The question is if it was the theoretical calculation or it was a measurement, right? So I would say that it was coming, I mean, the data is coming from the measurements with ellipsometry.
Yeah, Luis is putting your thumb up, so it's okay.
Okay, yeah.
So any other question before we move to the next things, the step? Well, if not, we could go for the photo that Sol mentioned before. So thank you very much, Sarah, for your presentation. Very good job. And right now, if you don't mind, please open your camera so we can take a screenshot. Okay, Irene, is that okay for you?
Yes, we can now take the picture. Okay, I take a couple of pictures. Maybe if you can also take, Victoria.
Yeah, I'm doing it. Okay, I got it.
Excellent. And we have a little souvenir. Okay, so shall we start with the next talk? We are a bit in advance.
Excuse me, I couldn't hear you for a second. Could you?
Yes, now I was just saying that we are a little bit in advance.
Sorry, again, I had a cut of the internet. If you can repeat, please.
Yes, I was just saying that we are a little bit in advance of a schedule.
Oh, yeah. Mm-hmm.
But maybe we can, yeah, it's just 7 minutes. So we can start maybe with the next talk.
Speaker. Okay, yeah. So next speaker is Iver Breivik, but I'm not sure if he already joined us.
I phoned him 20 minutes ago, and then he was going to log into a computer, but I haven't heard from him since.
So in that case, maybe could we start with?
He knows that he's supposed to speak at 11:30.
Yeah. So shall we take a 10 minutes break in order to wait for him, or we start with the next one speaker? Maybe
yeah, we can wait.
It's better to wait, I would say.
Yeah, okay. Better. Yeah, we have a 10 minutes break, so we can.
5 minutes.
5 minutes. Okay, 5 minutes break, and in 5 minutes we come back.
Yeah, George, it's saying that you can speak in the meantime.
Yeah.
If you want to discuss anything, you have these 5 minutes to interact between you. A green button.
Now it's just recording.
The button.
But you, well, button. You just click on record the session, but you need to share your screen, which is the green tab in the bottom part of your screen.
No, you can continue without me, because there is. I had the connection all the. Yeah, but I cannot shift page. Yeah, now it worked. Now I can shift page. What shall I do?
Sorry, sorry everyone, because I lose the connection for a while. Thank you, Iver, for finally joining us in your presentation. You can start when you want. Today you are going to talk about Casimir forces between ideal metals plates with a chiral intervening medium. So you can start when you want. We will appreciate it if you could make this short talk, because we should finish in like less than 10 minutes.
In 10 minutes.
So if you can do it.
That is okay.
Okay, thank you,
Yeah.
Iver.
Okay, sorry for this technical problem. I shall speak about the Casimir force between ideal metal plates when there is a chiral intermedium in between the plates. So the chiral medium is an extension of the usual dielectric medium in which constitutive equations are more complicated, so that the displacement D is equal to quantity proportional to the electric field E plus a quantity proportional to B. Conversely, the B is equal to something times the H plus something times the B. So it is in a more complicated thing. A very natural example in this connection is it is taken from astrophysics and for a connection with the axion field, which is a pseudoscalar, and which implies that when one goes to the Maxwell equation for that kind of thing, one sees that there is, in the presence of a magnetic strong field, there is a current, an electric current going on. The only difference lies in this Ampere equation, which says that the curve to E, the curve to H should be equal to J plus the time derivative of D. And in the presence of a magnetic field, this H, this electric current, is proportional to the applied magnetic field times the time derivative of the pseudoscalar axion field. And from an electrodynamical point of view, that is quite an interesting thing, because it means that the electromagnetic energy momentum tensor has a four divergence which is not equal to 0. So this means that the system is not closed. So there is a very dramatic difference as compared to what is the case in normal electrodynamics, where you have the Minkowski energy momentum tensor being divergenceless. So that the total components of the momentum and the energy do form a four vector when you are integrating over all space. That kind of thing is not present here, so that you have a non-closed system. That might be the reason why it is difficult. It has turned out to be difficult to construct a green function for this kind of medium. What I shall see is now, what I shall do now is to go to a concrete example built upon two papers, one by Dong Yang and Frank Wilczek from the last year, and also a small short paper which I wrote together with my collaborator Johan Høie in this year. So it is a normal standard Casimir setup in which there is a chiral medium in between two perfectly conducting plates. In the first case, we are looking at the 0 temperature, and Zhang and Frank Wilczek, they considered this point from a fundamental point of view, from a field theoretical point of view. Quite a long calculation, in fact, which I extract here in the final, more or less final form, namely that the energy at t equal to 0 is equal to this integral, in which you have the determinant to a quantity which includes a propagator between the plates A and B, and which includes the reflection coefficient at the two plates. So that that means if we then are assume that the plates are behaving in the same way as regards the reflection coefficient, then you get this reflection coefficient R A and R B to be equal. And the propagation quantities are given here, so that you have the propagation in the plus direction, is the plus z direction for left-handed polarization, and you have here the propagation in the plus direction for the right-hand polarization, and you have those two quantities from B to A and for A to B. So that is the main formulas which they are considering and elaborating on. And this theta is the rotation angle. It is quite similar to what I mentioned in convention with the axions in astrophysics, because this axion is essentially the phase of the complex scalar field in the early universe. And this constant V here is called the Verdier constant, which is given numerically here in the paper by Young and Wilczek. And by doing this calculation, quite elaborate calculations, they find this expression here for the energy at t equal to 0 between those two plates. And this is a normal or the conventional abbreviation for the wave number. This is the Motsobara frequency, and kx and ky are the components of the phase vector parallel to the plates. And when they are elaborating this kind of thing, they find this result here. And as I said, that was published last year in PRB. Johan Høie, my collaborator and myself, look at this from another point of view this year, from a very physical point of view, without going into so much heavy mathematics, but looking at from a very simple physical point of view, namely that the TM modes rotates into a TE mode partially, and the TE mode results into a TM mode partially, corresponding to a rotational matrix. This is simply the rotational matrix for a rotation along the z-axis, the axis orthogonal to the plane. And if one goes from one plate to another one, to the next one and back, one can either get zero result or one can get a double result. And the double result is what is materialized in this Fraunhofer, this Faraday effect, the rotation of the plane of polarization. So that what we did was simply to start from this very elementary expression for the energy between two perfect planes in a vacuum. And the number 2 here is an essential point because it reflects that in normal circumstances the TE contribution and the TM contribution are equal. And the essential part of the Lagrangian is the part here in which this factor 2 occurs. This expression for the normal electric in the normal metallic case can be written then in a block way, so that yeah, is it not reacting? Can I get down? Page down, it should react. Yeah, but what we it should good. Yeah, here it is. So this is a standard expression for a perfectly conducting case in which we have replaced the one by a block matrix here. And what we are doing is simply to replace this one matrix with this big A square, which is taking account the rotation of the TM and TE planes when propagating of the light along the z-axis. And this is easy to calculate. So one can calculate the determinant of this kind of thing and get this expression here. So that the result which we get is this one, which is identical to what Young and Wilczek found 1 year ago. But the difference is that we do not use almost any mathematics at all. We are only using a physical point of view, a physical argument, so that we simplify the calculation of Young and Wilczek in a quite impressive way, in a quite important way. So this physical way of looking at the system is due not to me, but to my collaborator, Johan Høie here in Trondheim. So this expression here can lead to a force which is attractive, or to a force which is repulsive, dependent on the value of the B of the electric field and dependent on the value of the Biennial constant, so that one can tailor the force between two metallic plates by adjusting the magnitude of the very strong magnetic field which is directed orthogonal to the plates. So this is a generalization of the standard Casimir theory to the case of chiral media made in a very simple way. And I think that also one very important application of this kind of thing can apply just in the astrophysical case, where you have this coupling to the magnetic field in the very early universe, so that this chiral field is a phase of the complex field which is occurring, I think, from 10 to the minus 10 seconds, and is propagating to this day. So there are many applications in the background here, both to the laboratory cases in which there are chiral media present, and to the astrophysical case. So I think I stop there. Thank you for the attention. I'm sorry for the delay.
Thank you very much, Iver, and thank you for this nice talk. And no problem with the problems. It's true that with this online we also all have problems. But well, if there are any questions, please for Iver, just read it. There is one question. I will read it out loud. Dear Iver, you speak about chirality, but you treat the Faraday effect. This is not the same, and not the same broken symmetry either. Did I misunderstood?
Yes, I can look at astrophysical case. In that case, the Lagrangian interaction part of the Lagrangian is equal to a Kaplan constant, which is very small. It is 10 to the minus 12 inverse GeV. And the reason for that is that one axion has to interact with two photons. So that is written formally in the sense that the interaction Lagrangian is equal to this Kaplan constant times the scalar field, the axion field, times the field tensor multiplied by its adjoint. And that boils down to a product of the electric field and the magnetic field. So there are two fields occurring here. So that is the reason why there are two photons involved. That is a pseudo-scalar. So that is the reason, physical reason, why this axion is a scalar field. So that in the interaction Lagrangian you have the product of E and B, that is a general field. But when I look at the application, I assume that there is only one magnetic field present, which means that the electric current is equal to the same Kaplan constant times this pseudo-scalar field times B, so that the electric current, in fact, is proportional, or has the same direction as a magnetic field, although the axion as such is electrically neutral. So I think it is quite a depressing point that one can use the same formalism as one does in the case of the electromagnetics or magnetic media, but take into account that the system is non-closed, so there is a source term, which again in turn has the implication that the total momentum and the total energy do not constitute a four-vector. Quite an important thing. It is a mirror of what is the case in the electrodynamics of media, where you have the Minkowski energy momentum tensor, which is divergence-less, which corresponds to the mentioned four-vector properties. But if you are going to the Abraham case, then you have just a kind of thing. You have a non-closed system, which means that the total energy and the total momentum do not constitute a 4 vector. So this
Okay.
is, yeah.
Excuse me. We need to move on and continue with the next talk. If you wish, you can have some discussion after the talks when we finish the next 2 talks.
Yeah.
So thank you very much for the question also. We are going to move on. Please, even if you could answer your screen in order to allow other speaker to share his.
Yeah, I should try that.
Okay.
Yeah.
Okay, so please,
yes.
Professor,
Yes.
he's the speaker, and he's going to talk about measurements of the Casimir force in a gas and in a liquid.
Okay. So I share my screen. Do you hear me?
Yeah, we can hear you.
Why? What happened? Why? I try to share the screen. Ah, okay. Allow. Why it does not allow? Screen. Okay. Sorry. Okay. And I'll go. What happened?
You cannot share your screen?
Yes. Okay. Sorry.
We are not seeing
Good.
your screen.
No, but it does not allow me to. Why it says that? Does not allow me to share the screen.
No.
What is that? No.
Let me.
I asked. Yeah.
You are
the. You know the switch allow is not blue as it should be.
Okay. Yes.
Did you allow?
You have privilege of being co-host, but I will do it again just to.
Yeah. Okay, I'll start again. Sorry, probably it will work better.
Yes, you are co-host, so you should be able to share your screen.
Yeah. Now it's completely stuck. Okay, let me.
We don't know if Iver closed properly his share screen, but I don't think he's in the list of participants.
Yeah.
He closed properly. Because now I can see you as participant.
Okay, do you see me? Okay, let's see the screen. Again, select the screen, and then I have. Okay. Okay, now it works. Okay, good. Do you see my screen?
Yeah, we see it.
Yes, now
okay,
we see
good.
it.
Now, see, okay, so I put the full screen, okay. So I joined, so can you hear me? It's okay.
Everything's perfect, thank you.
Okay, good. I want to join the other speakers. That was a very good idea to start to organize this workshop online. Okay, I like online workshops, although I mean we have not these very nice things that we can discuss with the people after the talks. That is part. Probably is the most interesting part. Okay, so this is a work that is mainly done by Le Cuneder during her thesis, and there is a collaboration with Italy and George that we heard a few minutes ago. Okay, so let me give you the motivation of this experiment. As you heard yesterday and today about the Casimir, the critical Casimir, we were mainly interested in the study of the critical Casimir. But then it happened that we wanted to do some calibration, and we thought that in Casimir, standard Casimir, everything was clear. And then we realized that was not so clear, and then was the reason of the collaboration with Vitaly and George. So let me make the point. So in this audience, I don't need a long introduction, but I just remember that Lifshitz and co-worker in the 50s computed the Casimir force in the more general case of Casimir, with real dielectric plates separated by another dielectric materials, and then we know by combining these dielectric properties we can actually tune the Casimir force. But now we know, we had the previous talk by Zara, that indeed for real surfaces there are problems because which are related to the roughness, to the final conductivity, and so to the knowledge of the material optical properties that can strongly alter the Casimir force. In liquid, the determination of the Casimir force is even more complex because, as we know, because of electrostatic effect, we can have a stochastic effect and the ions that are in polar liquids. Then we can have formation of screenings that are called the bilayers that forms along the conductive plates. So we wanted to understand a little more about all of this, and so we designed an experiment to clarify this problem in a situation in which the experiment we can change easily between, for example, a gas and a liquid. And so, I mean, what I will speak about, we measure the Casimir force before in a nitrogen atmosphere. And then using exactly the same system as you will see later, we will measure in ethanol. And then this is a big advantage because the contact area and the roughness are the same in both measurements. So what we are really testing is the other properties related to the bilayers and to the change of the electric properties of the material between the two plates. Mainly, I mean, just I give you the main results of what I will talk about. We find that the electrostatic force screened over the Debye length, of course, are of the same order of magnitude of the Casimir force. And then, as you will see, we highlight the importance of accurately characterize the optical properties of the sample before a minimal comparison with the theory. So this part will be close to what Zara said. Okay, so my talk will be mainly experimentally. I will tell you what we did. Okay, so the key points that we have an AFM cantilever on which we glued a sphere. And the properties of our AFM, home-made AFM, is that the measurement is done by interferometry. So we actually, the reference beam is on the point where the lever.
Pardon.
Sorry, yes?
Are you sharing the presentation? I mean, have you spanned the presentation?
Yes, you don't see the. Yes, I'm sharing. Wait.
I mean, that is. You need to select each slide in order to us to see it, because we were not watching the slide you were showing.
No. Wait.
See your full screen window. We only see the PowerPoint window.
So you don't see this?
We now see your slide, your fourth slide, but we don't see the slides moving. If you were talking before and you were moving the slides, we couldn't see. How do you?
Okay, so I'll stay like this. It's good enough. I don't.
Yeah. It's good enough. And also, if you prefer, you can also put your camera just if you want.
Yeah. Okay. It is not on.
No.
Okay. Sorry. I thought that it was. No, it's not on. Sorry. Okay. It's okay. Okay. Now I see.
Now we can see you. Yeah. And in order for us to see your slides, you need to select each one. Okay.
Yeah. Okay. It's good.
Okay.
Yeah. Okay.
Can you move to
so do you see the fourth slide? Okay.
Yeah.
Okay, so here the specific point is that we have the reference beam that is on the point where the lever is clamped, and then the measuring beam is on the top of the lever. And so by making interference between the two beams, we can measuring exactly the deflection of the beam. And this allows you already to reduce the number of calibration that you can do, because this is, of course, self-calibrating. Then, okay, in this small sketch, I saw the problem of the roughness that actually introduce an extra distance between the surface of the sphere and the plate, okay? That is actually given by the mean height of the plate. The characteristic of our interferometer are very, very good, because we have a noise level that is around 10 minus 14 meter per square square root of Hertz. Okay, so what I was saying, I mean, the other specific point that everything is inside the cell, that actually is closed, and it allows to be filled either by nitrogen and either by nitrogen or ethanol or a liquid. And the other specific point that if the plate is semi-transparent, we can also detect with evanescent waves the distance between the sphere and the plate. Okay, here we have a small picture of the experiment, okay, and just to recall all the feature, we have our sphere is 75 micron radius, so is a rather big spheres in order to have a good signal to noise ratio. The stiffness of the cantilever is 0.5 Newton per meter, which is calibrated in different way. As you know, this is a very important point, because all the accuracy of the measurement comes from a good estimation of the stiffness. So we use two standard methods that are related either with the variance of the oscillations in the thermal oscillation of the cantilever, or fitting the spectrum with an oscillator model, or with a more recent method that we recently published in Europhysics letters. Okay, this is the cell, as I said, and then we did the experiment both in nitrogen and ethanol. Okay, so as I said, I mean, the problem of the roughness is very important. These are two scanning electron microscope images of the sphere. And then we have that, as I said, has a 150 micron of diameter. So as was mentioned before, using another AFM, we characterize the roughness of the sphere. And so here an image of the surface of the sphere. This is the probability distribution function of the 8 of this roughness, and the correlation function that is around 200 nanometers. And okay, the roughness of the sphere is around 11 nanometer, whereas the roughness of the plate is about 1 nanometer. And so we use at this point for D0 3 times I mean, for the real distance that I define as the distance measured by the piezo plus the D0 and minus the deflection of the beam of the cantilever, then this we use for D0 3 times, which is reasonable to think that is around 3 times this roughness, okay? So the other point, as was mentioned before, was about electrostatic interactions. And for doing that, we use, one of the methods is to excite the cantilever with oscillating electric field. And then as the response is quadratic, you can make a difference between the contact force, the contact potential, and the other potential. I mean, then you have quadratic response at 2 omega, but you see that if you make the measure at omega 1, that is the exciting frequency, you can extract immediately the amplitude of the contact potential, that in our case is constant as a function of the distance between the surfaces. So I will, okay, and then as usual, what you can do, you can use electrostatic, the second harmonic in order to measure the electrostatic interaction. But you can also do directly by measuring the shift of the resonance of the resonant peak of the cantilever. You see that now this is shifting, and the shift, of course, is given by the gradient of the force that has 2 components, as Casimir force and the Casimir gradient plus the terms that is coming from electrostatic interaction. So we have these 2 methods that we used, and this allows us to determine exactly the position of the sphere with respect to the plate without touching it. And okay, and this was very nice because we found around 31 nanometer that is close to what we had estimated, that is 3 times the standard deviation of the roughness of the bead. So after doing all this calibration, in the case of the nitrogen, the hydrodynamic correction related to the viscosity of the nitrogen are negligible, taking into account also the speed in which we are moving the plate versus in the direction of the sphere. So this is the result of our measurement. So you see this, the blue points are the experimental points average over many sweep on distances, and these are the various theoretical prediction. The red one is the run by in the case of ideal conductor that is very far from the reality. The green curve corresponds to the Lipschitz theory, in which the electric function is evaluated using input optical data. And this is instead the red curve that actually is fitting quite well the data, are real measurement of the optical data on data on real gold film with roughness close to what we have measured. So you see that the agreement is very good, and okay, this is plotting log.
5 minutes left.
Yes. How much?
5 minutes.
5? Okay, fine.
Yeah.
Okay, no,
Okay.
but it's okay. Yeah, thank you. So as you see here, I mean, on the right panel, you see that indeed the difference is very important, because this is just the difference between the experimental data and the theoretical predictions, and then you see that indeed the measure optical data actually fits quite well on the experimental data, whereas the handbook data actually deviates of about 10 piconewton. Okay, this is for what for concern the nitrogen, and then okay, as I said, we fill the cell with ethanol without changing the alignment, and so keeping all the rest constant. Okay. So we didn't even shift the surface. So as I said at the very beginning, we are actually testing in the liquid the same area in which we did the measurements on nitrogen, okay? Now, the real problem that we have to suppress the hydrodynamic interaction that in this case cannot be neglected and has to be subtracted. So to do that, we did in a very simple way, as this is the hydrodynamic force that contains the speed, the vertical speed in which the sphere is approached to the surface. Okay, but now you see that you have plenty of other, as I said before, you have plenty of other forces. You have the electrostatic forces, you have the Casimir forces, and so what you do measurement at two different velocity in such a way that you suppress completely all the other forces that do not depend on the velocity. And so this is what we did. This is the hydrodynamic interaction as it's measured. You see that this goes as 1 over d. That is what the hydrodynamic force tells you. Okay, this is traced in 1 over the force. And so this again allows us to estimate the effective distance of the system. And then you see that this is very nice, because it's a confirmation of the electrostatic measurement that gave us about 30 nanometer. And here we refined again, well, the fact that it's exactly the same is of course accidental, but is within experimental error, is around the 3 times the roughness of the sphere. Okay, so we were very happy about that. So now what we do, we can subtract the hydrodynamic interaction from the total measurement. So we did we approach the sphere at 100 nanometer per second. So as we know now the coefficient, we can subtract the hydrodynamic interaction. So this is what remains, okay? You see, these are the experimental points, And then, okay, so you have to keep into account that there is, as I said, the bilayer that, and so the electrostatic force, which is screened by, as I said, by the bilayer. So this is the standard expression. The important point here that you have this an exponential behavior. So we fit this exponential behavior for distance larger than around 120, 150 nanometer that, as you will see, is good enough to avoid the influence of the Casimir forces. And then what we find that the characteristic wavelength of the bilayer is around 47 nanometer. And you see that this voltage that indeed should be related also to the contact potential is just a little smaller than the contact potential that we have measured in nitrogen. And this is of course the case because we have ions inside inside the fluid. Once you have done this, you subtract also the bilayer. The electrostatic interaction screened, by the bilayer. And so this is what you find. This is for a single measurement, okay, which is already quite good. And then you average over many measurements. And okay, here you see that there are the dots are the mean force. This is the measured optical data. And keeping into account also the electric constant of the ethanol, okay, and then this again the handbook of optical data, and then again I plot this on different, as I said before, and you see, okay, the error is of course a little larger because the force here is smaller because it's screened by the electric constant of ethanol, but still you see that the measured optical data actually fits better. The experimental data than the handbook optical data. So I conclude here, okay, just to recall what we did. We have measured in the same experiment the Casimir force in nitrogen in ethanol, and the measure roughness, the hydrodynamic electrostatic calibration, allow a precise evaluation of the minimum sphere plane distance, and the Landau theory fits the data using the measured values of the dielectric constant. The force measurement yield experimental evidence of the importance of the electrostatic effects in ethanol. So I'll stop here and thank you for your attention.
Thank you very much for your nice presentation. So now questions are open. If you have any question, you can write it down in the chat. There will be a few questions. I have a question myself. It would be possible to correct the hydrodynamic force for large viscosity fluids, as it is, for example, visceral, or in that case, it's going to be harder to correct that?
No. It's not harder. Actually, the problem is probably on the other way around. The hydrodynamic interaction will give you a lot of error on the estimation of the Casimir forces, because then you have to subtract. So you subtract a very large contribution to the global force. So to the total force. But in principle, I mean, you can do. But actually, I didn't say, we did also on the other way around. Indeed, also the measurement in nitrogen has been corrected for the hydrodynamic, because when you are close, indeed, although you are in air, I mean, the viscosity is very, very large, because you see that it diverges 1/d. So the viscosity, the contribution of the viscosity becomes actually very, very important.
Yeah, I see. Okay, there are 2 questions more. The first one is from Louis McDowell. The Casimir regime with Casimir exponent should be reached earlier in the ethanol than in nitrogen. Could you confirm this from your experiment?
What is it that should be reached earlier? What do you mean? Why early? Okay, the point is I don't understand what you mean by earlier, because what I've shown is that indeed I would like to understand what means earlier, because it's clear that for distance that are shorter, see, earlier means this,
Yeah.
it's okay. Yes. Yeah.
Okay.
Yeah, you can see here, I mean, okay.
It's okay, Luis?
Do you see? Yeah.
No, he says, meaning at smaller phase separations, the crossover length could be related to the inverse of refraction index, no?
Yes. And this is the case. You see that here the same forces are obtained for much shorter distances. Is exactly what I'm saying.
And he says, is this a comparison of nitrogen and ethanol?
Yes, in some way, yes, it is. It is a comparison between nitrogen and ethanol, because as I said, indeed, we use exactly the same surface as between an experiment and the other. We did not even shifted the plate with respect to the sphere. So we are actually measuring the same point.
Okay. And there was another question about, well, made from Bart van Stiegelen. Is the eternal problem that causal polarizabilities do not seem to fit? Sorry, I can read it
I
again.
don't understand what you mean with that.
Maybe Bart, you could
Hi,
please
Bart.
open your microphone.
Yeah, sorry. Yeah.
Excuse me, Bart. Would you mind
The fact
to open
that
your
the input is wrong. Yeah, I don't know. I mean, that we use the data of Italy and George, and I mean, as you can see, especially in nitrogen, there are no doubts that the fit is much better with the real data than the handbook data.
Okay, thanks.
Yeah.
Okay, so thank you very much, Sergio, again. We are going to move on to the last speaker. If you don't mind to answer your screen, please.
Yeah.
And next speaker is Juan Luengo Marque. He today is going to talk about van der Waals forces at the ice surface with an update description of the dielectric responses based on the Theorem model.
Hi, hello. Can you hear to me?
Yeah, we can hear you, and we can see your screen.
Okay, now it's in presentation mode. Do you continue seeing as I switch the slides, right?
Yeah.
Okay, fine. Then I will start. Well, hello everyone. First of all, I would like to thank to the organizing and to the scientific committee for the opportunity of presenting here today. My name is Juan Luengo, and I would like to present this work entitled Van der Waals forces at the ice surface with an updated description of the dielectric responses based on the Drude model. It has been performed at the Complutense University of Madrid, and as Professor McDowell has previously presented this point of view of the Lipschitz theory and how to approach those equations, gaining a better insight and better understanding on how these the crossover from London to Casimir interactions work. Here I will focus more on the dielectric functions, the description of the dielectric responses required for the Drude model. And well, first, let me introduce the motivations, the main motivations for this study. First, the ice surface is covered by a thin pre-melted water layer at the ice-air interface, which govern a wide variety of phenomena related to the growth of ice. Among all the contributions to the surface free energy, this study, as I said, will focus on the one of the long-range van der Waals forces, studied in the framework of the Lipschitz theory, which, as Professor McDowell has already explained at the beginning of the day, covered from London to Casimir interactions. In this framework, again, Elboom and Schick published back in 1991 a widely extended study in which they predicted the stabilization of this pre-melted water layer just from the contribution of the Hamaker of the van der Waals forces. As they performed their study, having an incomplete description of the optical properties required by the Lipschitz equation, I will show in the following slides how the landscape changes according to the new updated experimental data. So, to begin with, in principle, the common view of the van der Waals forces obtains them summing the interaction energies between pairs of particles, which for a three-layered media geometry like the one schematized in the diagram of this slide, provides a contribution of the van der Waals forces to the surface free energy that decays at the inverse of the distance of separation, this h squared. The Hamaker, the interaction coefficients between pairs of particles add to get this Hamaker constant, h sub ham, which has the opposite sign to that of the surface free energy. Well, this was the common view of the van der Waals forces, and on the contrary, the modern view through the Lipschitz theory understands them through the simultaneous dissipation of electromagnetic waves between the interacting materials. So that the first consequence of this is that as the dissipation does not happen exactly at the same time in all of the interacting substances, this actually, due to the finite velocity of the light, this actually turns the previous Hamaker constant in a function of the distance of separation, as it appears in the equation highlighted in this slide. The next formula is a simplified version of the Lipschitz equation, in which I show what is the cornerstone of the Lipschitz theory, that the sign of the Hamaker function, and therefore the sign of the van der Waals interactions, whether if they are attractive or repulsive, depends on the relative differences between the dielectric responses of the substances that are interacting. They are this epsilon that we can appreciate in the formula. So the next step will be, of course, to characterize the dielectric responses of the substances we are considering for the ice-liquid-water air system. The dielectric responses of ice and liquid water will be characterized by means of the Drude model, which express them as a sum of Lorentzian oscillators, each of them described by a set of parameters. As it is possible to separate this expression of the Drude model between the real and imaginary part of the complex dielectric response, and both are related with experimentally available extinction index, we can get the parameters that we require to describe the dielectric response from a numerical fit over experimental values of the extinction index and its evolution with the frequencies. And that's what we have done. And finally, when you evaluate at the original Drude model equation at imaginary frequencies, we reach the dielectric responses of these substances, taking only real values. And this is the way we will use them for the calculations of the Lipschitz theory, because it is easier to compute this way. And here, the last line, here I summarize what I have been explaining so far. Reading it from the right to the left, we have performed a wide bibliographic review of the extinction index of liquid water and ice in order to, through a numerical fit to those experimental values, we have reached the dielectric responses of liquid water and ice. And with that, we have calculated computed through the Hamaker equations, the Lipschitz equation, the Hamaker function of the ice liquid water air system, and the contribution of the van der Waals forces to the surface free energy in this system geometry. Well, then when Elboom and Schick performed their parameterization, as I have described it, for their aforementioned article, the experimental data they had didn't complete the evolution of the high energy band, we can appreciate this. Well, it is this red line, and it don't complete the evolution of the high energy absorption of the extinction index as a function of the frequencies. This is why in their adjustment they assumed a rapid drop of the absorption in this region, the most important one for the calculations, by the way. It is their adjustment is their fit is represented by this blue line, and in a relatively recent article published in 2015 by Hayashi et al., they shown the actual evolution of this high energy band, and that the drop is much slower than the one assumed by Elbaum and Schick. And this has a very strong consequence on the description of the dielectric responses. With the lack of those values of the extinction index at high energies, Elbaum, the dielectric function of ice provided by Elbaum and Schick overtakes that of liquid water at the high energy region, the most important one in the calculation of the Lipschitz theory. While once we include this updated evolution of the high energy band, we reach that the dielectric response of liquid water is always larger than that of ice for the entire range of frequencies. Except, of course, for the static contribution, the zero frequency contribution. And well, this has a very strong effect on the Hamaker functions, because, as I said, their sign depends on the relative differences between these dielectric responses we are seeing here. But still, there is one more thing to say in favor of the Elbaum and Schick's work, and it is that the experimental square refractive index that their square refractive index before ultraviolet absorption, the one that they predict from their study, has the value of 1.76, and it is very close with the experimental compared to the experimental 1.77. Especially compared with the one predicted by this work, 1.93, which is far away from it. So the question, of course, is how, employing an updated experimental information, we cannot fit this experimental value. And the answer is that there is an inherent inadequacy to the truth model, and it is that it overestimates the values of the extinction index at the left tail of the high energy band for both liquid water and ice, due to the slow drop of the Lorentzian oscillators. We can appreciate this in these figures for both ice and liquid water, respectively, and from the left to the right. And comparing this red line, the parameterizations based on the truth model, with experimental values represented by the black dots. It is clear that if we cut the overestimation employing a Heaviside or a step function at the imaginary part of the dielectric response, we will cut it as it is represented by the green lines in these figures. But this wouldn't fulfill the causality imposed by the Kramers-Kronig relations. And that's why in this work we have developed the complex step function, which is able to amend this, to modify this, to correct, better said, this overestimation. It is defined analogously to the complex dielectric function, and with a real part that goes from 0 to 1 at a cutoff point, at a cutoff frequency, as a non-analytical heavy function will do, Heaviside function will do, but with an analytical form, with an analytical expression. But it has also an imaginary part that starts with a decay as the inverse of the frequency and switches at the cutoff frequency to 0. Taking all both together and applying them to the set of B parameters of the truth model, the complex step function is able to correct, to amend this overestimation, leaving just the contribution of the cutoff frequency of those oscillators to which it is applied before the cutoff point. And once we evaluate it at real frequencies, separating the real and imaginary part of the truth model, it produces the same cut on the imaginary part of the dielectric response that a non-analytical Heaviside function will do, as it was previously represented by this green line. So overall, its effect is that before the cutoff point, before the cutoff frequency, it lowers the dielectric response proportionally to this overestimation that it is cutting. Here we are representing the real part of the dielectric response with respect to the frequency, and beyond the cutoff point, the cutoff frequency, it leaves the parameterization of the truth model untouched. It doesn't modify the truth model at all. So Of course, its validity must be proved via Kramer's conic relations, and that's what we have done, applying them directly over the experimental values of liquid water of the extinction index. And from the comparison in this figure, we see how the green line corresponding to the parameterization of the Drude model corrected with the complex step function is superposed or almost superposed to the parameterization based on, with the predictions of the Kramer's conic relations, this black line. While the Drude model alone, the red line, is not able to fit so nicely the predictions of the Kramer's conic relations. So this will be the proof that this complex step function we have developed works. And with this, I present here the Hamaker function of the ice, liquid, water, air system, the resulting ones. On one hand, in Elbow 6 work. Sorry?
5 minutes left.
Ah, okay, thank you. On one hand, we have that in the Elbow 6 work, as the dielectric response of ice overtakes that of liquid water at high energies, the Hamaker function they have presents a change in the sign. But once we have corrected with the complex step function the overestimation over the parameterization based on this updated experimental information, we reach that still the dielectric response of water remains larger than that of ice for the entire range of frequencies. So that the Hamaker function we present in this work is generally positive, meaning that the ice feels attraction with the air across liquid water, so that the liquid water layer becomes thinner between them. And on the contrary of what Elbaum 6 predicted, it reveals that the van der Waals forces are not able to stabilize the thickness of the liquid water layer on their own. So finally, and before going to the conclusions of the work, I am going to present here a brief comparison with a very recent article published this year by Fila et al., in which they presented, among many other interesting things, a very accurate parameterization performed over the imaginary part of the dielectric response, obtained via Kramer's conic relations with experimental data of of the extinction index of liquid water, including as well the updated experimental values we have used from Hayashi. And they employed, trying to cope with the insufficiency of the Drude model, they employed a large number of oscillators, more than expected absorptions, trying to fix it. But as we can appreciate in the figure on the left hand, representing the adjustment in the imaginary part of the dielectric response, they couldn't fix completely the overestimation, achieving a value of the square refractive index before the ultraviolet absorption of 1.85, still better than the previous 1.93 of this work, but still far away from the experimental 1.77. So once we correct the overestimation employing this complex step function on our parameterization, we reach a value of the square refractive index before ultraviolet of 1.774, extremely close to the experimental one, not being necessary to change the parameterization and not being necessary to add an additional number of oscillators. And I want to mention as well that probably the value they get is the best that one can reach employing only the Drude model, because this overestimation is inherent to the Drude model itself and has nothing to do with the parameterization. So that's how I justify that it is required the addition of an additional function in order to correct it. So, and with this, I will summarize the main conclusions derived from this study. First, the exact Lipschitz result for the three-layered media geometry has been used in order to study the ice liquid water system. For that, we have performed a characterization of the dielectric responses of liquid water and ice by means of the Drude model, employing an updated experimental data of the extinction index, and being aware of the insufficiency due to the overestimation performed by this slow drop of the Lorentzian oscillators of the Drude model, we have developed what is the main novelty of this work, this complex step function that turns out to correct the overestimation, achieving the best accordance ever made with the experimental values of the square refractive index before ultraviolet absorption. And finally, the last conclusion will be that the van der Waals interaction do not promote the stabilization of the thickness of the liquid water layer at the ice-air interface. Instead, ice and air experiment attraction across liquid water. And finally, the role of the short-range interactions is also required in order to complete a study of this kind of systems, because we have been only dealing with long-range van der Waals contribution. And with that, I have finished. Thank you all and very much for listening. And if you have any question, I will be glad to answer. Thank you.
Thank you very much, Ham, for your presentation. It has been very interesting. Let's see if there is any question in the audience. Yes, there is the first one from Svetovoy. What is the importance range of distances? Could be the retardation important?
Sorry, the last part?
Sorry, there was two questions in the same one. The first one is, what is the important range of distances? And the second one is, could be the retardation important?
Yes, of course, the retardation is important. In fact, what we are seeing here is that the Hamaker function, as I said, is a function indeed because of that retardation effect. And therefore, the important range of distances depends on the indeed on this retardation effect. On one hand, we can expect that its maximum value and at very short distances it remains constant because we will be in the London regime. But here the contribution of the short range interaction will be absolutely dominant. So the values of the distance in which we expect that the van der Waals interactions are relevant include include some a portion of what it is affected by the retardation effect.
Okay, thank you. I think the question was answered. Are there any other questions? It seems no. So, well, in any case, you know that after this session, this Zoom session is not going to be closed until 1:30. So if you want to discuss anything else, you can do it. So thank you very much again for your presentation, Juan. With this, we finished this mini colloquium with the that has been devoted to the Casimir effect and the heat transfer advances. And let me put the video also. So just to wrap up this mini colloquium, I just want to thank you, all of you, for being here. We have been more or less between 30-50 people every day, so it's more than I expected at least. So I'm very happy that you all were interested in this mini colloquium. Although it was in the end an online conference, I hope it was fruitful for all of you and you could learn something else and you well, learn about what is people doing right now in this field. And I just want to also thank to Irene for being the host of this session and being all the time keeping an eye on what we are doing. And also I want to thank the overseas participants because they were getting up very early, or people from the other side that were going to the bed very late. So thank you very much for your participation. And well, in the end, the schedule was not very strict, but it was quite strict during the first day and the first part of the day. So thank you also to all the speakers for being very tight in your time. With this, I just want to say again that thank you all of you. I'm going to give the microphone to the rest of the co-organizers if they want to say anything else. Just that, thank you very much to all of you.
Thank you, Victoria.
Thank you for having organized this.
It was a great pleasure. It finally worked out pretty well, I think, despite the situation. And I hope we can see in person in the next conference soon. Just take care. We need to to pass it and wait until the next time we can all be together, and maybe it can be fruitful in a different way. No, I'm also missing the coffee breaks, the discussions, no, after the talks. Not the coffee, not the I mean, the discussion around it. But I think it was good to continue. We had the option to stop this mini colloquium, and we decided to try it. And I think it was a good decision that we did it, and we all could share our research, nowadays research. So maybe Mauro or Matthias or anyone can say something else. So thank you. George.
So can I say something to all of you? I wrote also a message. I think we should organize in 2021 a more extensive. This has gone very well. We can adapt more to interact more, you know. Like
yes,
as we are
also,
we should do that.
Also the schedule, I would say we really tried to make it possible that people from overseas could join us. So we tried to, instead of having 2 days, the mini colloquium in the morning, to have it in the evening, so that, yeah, in the end we could all be here at a normal time. But it was not possible. We really pushed about this, but there was no option, and yeah, and people did this effort, like Sunasi and Jeremy and some others. So I think it's a good idea. I also read what you wrote in the messages. This is more, so everybody can do this. So if you don't have a I don't know, maybe many people from the same group can join this, no? And sometimes because you don't have so much money in your project or whatever, it's not really possible to attend the conference, all the people that would really want to join this. But at the same time, there are some parts that are missing, I would say, and as you are saying, George. But I think it was a nice test. This was my first online conference, and I think it was great, and we can improve it. So this is more, it's for everyone, I would say, no? And I like this idea.
Yes, absolutely, yes. It went very well. It was a successful experiment. See it like that. This is how I see it.
Thanks.
Yes.
Okay, and I'd like to thank everybody also, and it has been very interesting talks, at least to me, and I'm looking forward to discuss with Juan and Luis about ice water later on in private. Thank you.
Of course, Matthias, and thank you, Victoria, Sol, Matthias, and I don't know Maura personally, but thank all of you for the organization of the mini symposium. And I think that this cannot match a nice conference where people are there, but it can complement other scientific meetings, and for small workshops in which we could, for example, discuss here like in a grid mode and so on, and share folder, I mean share the screen. This could be very interesting for discussions eventually. So I think there is room for this kind of meetings even without the coronavirus problem.
If I can say, so I would like really to thank all of you. First of all, Sol and Victoria, who did a real hard job in organizing all that. So thank you very much. And all of you for participating. It is a new kind of conference. It's my first conference online, so it's not bad. Honestly, I appreciated it. It's not the same as you are personally in front of people, but it's very nice. Okay, you can organize your time. You can do several things. Honestly, I appreciated it, even if it was not planned. And just to continue on the request by George of other kind of similar seminar on the same line, or in general on this topics, which is Casimir and heat transfer. I would just to say that, okay, it is not still official, maybe in 1 day or 2 days it will be official, but you know that there is a program, a Kavli Institute of Theoretical Physics in Santa Barbara. This is a very nice institution who allows for conference during 2 months. 2 months of conference. People are financed to stay there. So this institute pay you for your stay there, give you a lodging, and so 3 years ago I started applying to this. So I did three different applications, and it seems that now this year it worked. So it's not yet officially, maybe today or tomorrow we will know the official answer, but it seems that 99% it is okay. So in principle, it's been accepted. And so we will have the possibility from June, July 2022. So in 2 years from now, to have this 2 months program, which will be exactly focused on these 2 topics, Casimir effect and heat transfer. So it is really a wonderful opportunity. People can really stay there, discuss each one will have his own office, and you can discuss the whole day on these topics. And the idea is to have people from different community. We already contacted a large number of players, both in theoretical physics, in computational and experimental physics, in heat transfer, engineer, physicists, because we have several common problems. And the idea is to find a common language and try to solve this kind of problem. So this has been done in collaboration, this application with Ricardo Deca, with David Dean, and with Alejandro Rodriguez, this last submitted program. But in the past, when I tried to have this financed in the past, also Kim Milton played a crucial role, and also other people. So it's really the result of a collective effort of the community, and this is very nice. I think that we can all enjoy this if it will be really accepted, but I think that it will. So this will be maybe a possibility to join all of you personally in 2 years.
Okay, thank you, Mauro. We will keep an eye on that. You can also send an email to us.
When it will be officially accepted, I will send you an email, and people should submit. The problem is that only 25 places are possible, typically 25 for the people. If people can stay 2 months, this is more easy to be accepted. But if people can stay only 4, okay. I also have to add that I've been there 2 years ago. I've been invited in another program on quantum thermodynamics, and they've been there for 5 or 6 weeks with my family, with 3 kids. So this institution allows you to go with your family, and they take in charge everything. The stay for you, for your family is wonderful. They have activity for kids. They have a special building. It's really wonderful. So it's done for families. It's done for people which goes together with others. It's really nice. So there is a building which has been done recently in which all people is lodged inside, and you have blackboard everywhere. You have a floor of 1,000 meters square where you can discuss. There is a big garden with barbecue. You can do whatever. It's really a wonderful place. So
it looks really nice, but you need your family committed to your scientific
research. So I will go with in this case, I will go with my family for 7 weeks in US exactly for that. And you can come with your husband or wife and with your kids. And this is really appreciated. And so people who come from long periods and also with other people are people which more probably will be accepted. Okay, this is the strategy of this institute. So it's not me that I will be doing so I will suggest invited people, but I will not do the final decision. So it is KITPs, the University of Santa Barbara, who will make the decision and will invite people as invited professors. So also officially, these guys will be really invited professors for 2 months in this university. It's really nice. So please apply, and of course, underrepresented people will be appreciated, and we will do our best to prepare this program.
Great. Okay.
Okay.
I think I'm leaving.
Okay, thank you.
Thank
Okay,
you all.
thank you everybody, and thank you.
Thank you, everybody. Bye.
See you.
Bye-bye,
Bye.
everybody. Thank you.
Bye.
Bye-bye.
Thank you.
Bye. Thank you.
Bye. Thank you.